Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In our earlier videos, we were dealing about various electronic effects, right? Like for example, we have started off with inductive effect. Next is hyperconjugation. Next is resonance. Resonance sometimes is also known as mesomeric effect. Like for now, understand resonance and mesomeric effect as one and the same. Resonance effect or mesomeric effect. So these were the three types of electronic effects we have studied till now. One is inductive effect, next is hyperconjugation, next is resonance effect. So if I try to give you a brief introduction about or a brief idea about what these effects are, just to brush up our previous concepts. Inductive effect was polarization or the permanent, inductive effect was kind of a permanent effect, right? And inductive effect was polarization across a bond itself. For example, if I'm saying carbon, sorry, let me just make it more clear for you. If I'm saying a carbon chain is there and to it some group X is attached, okay, any hetero group X. Now what happens? There is electronegativity difference between this carbon and the hetero atom. As a result of which what happens? For example, let me consider this X to be more electronegative than the carbon atom. Hence what happens? This X tries to pull the electron density more towards itself. As a result of which what happened? It will not take up the entire electron density towards it, right? It will just cause a partial polarization. So some of the electron cloud which was uniformly or which was supposed to be uniformly shared between the carbon and X is now slightly shifted more towards X. Due to this, what was happening? X was acquiring a partial negative charge on itself and carbon was acquiring a partial positive charge on itself. Now this positive charge which is deficient in electron, so this tries to somehow compensate the effect of this deficiency by withdrawing electron from the next available bond, that is from this carbon. And now this carbon again develops. Now see, although this carbon is positive charge, it will try to compensate the effect somehow by pulling the electron density from the other carbon, but at the end both of them are carbon only, right? They have very less electronegativity, like no electronegativity difference. So as a result, the pull that carbon number 1 will exert on carbon number 2 is very minimal as compared to what X will exert on this carbon. So as a result, this pull will be much less than this carbon and X. Okay. So if delta positive is a charge which was developed on this carbon, on the second carbon the charge developed will be delta positive, means very even more lesser than this delta positive. Now this carbon somehow will get a deficiency of charge. Now to compensate that, it will try to pull the charge on this carbon atom. So now this carbon atom will again develop another delta positive, means very lesser positive than the second carbon also, and mostly after the third carbon this effect dies out. Okay, this effect is not evident after the third carbon mostly. So this was all about inductive effect. Now depending on the group, inductive effect was broadly classified into two types. One is plus I effect and the one is minus I effect. Now if I say plus I and minus I, so plus I was pulling the electron charge away from the group, or basically the group which was attached that acted as a donor of electron. That group donated electron to the carbon chain, as a result of which it acquired a positive charge on itself, and that group came to be known as a plus I group. Now if I see minus I, then the group that draws or withdraws electron cloud towards itself and acquires a negative charge on it is known as a minus I group. Okay, this was inductive effect. Now if I come to hyperconjugation, hyperconjugation was also somewhat similar to inductive effect, but that was occurring, or no sorry, hyperconjugation is not similar to inductive, it is somehow similar to resonance effect. But resonance occurred in a pi bond setup, but hyperconjugation occurred in a sigma bond setup. Basically in hyperconjugation what was happening? A donation of sigma electron was taking place to the deficient atom, as a result of which the carbon hydrogen bond was somehow like appearing to be broken down. This HH and H, if there is a deficient carbon over here, then this electron, sigma electron cloud was shifted onto this carbon atom, and this bond was seeming to be broken down, although it is not completely broken down. Therefore, it is called as no bond resonance. Okay. And this, and another thing to remember here is this proton was this H, which was like breaking down from the carbon skeleton, was not getting removed as a proton, but it was kind of staying near the vicinity of that particular system only. Okay, this was hyperconjugation. Now if I see resonance effect, resonance was basically delocalization of pi electrons. Hyperconjugation was delocalization of sigma electrons. Resonance was delocalization of pi electrons. Now for resonance to occur, the primary condition was presence of conjugation. Conjugation means alternate single bond and electron source. That electron source can be pi bond, lone pair, or negative charge. Got it? Now if resonance is happening, like if there is a group present and that group tries to draw the pi electron towards itself, as a result of which it will act or it will acquire a minus charge on itself, negative charge on itself, then that group has the tendency to carry out minus R effect, or I can say minus M effect, negative resonance effect or negative mesomeric effect. A group which tries to pull the pi electron density towards itself will result in a minus R or minus M effect, and a group which has the tendency to donate its lone pair or negative charge to the pi chain or the conjugated chain, then that will exert a plus R or a plus M effect. Okay. Now let us move into, this was a brief idea about all the three electronic concepts. Now how together we can apply these electronic concepts or electronic effects in studying the structures or stability of organic compounds, we will deal with in this video. So first of all, there are three permanent effects. In most cases, the dominant one is mesomeric or resonance effect. If you remember, I have said we were studying the effects in their ascending order of importance, like inductive effect, then hyperconjugation, then resonance. Okay, basically we were studying them in their priority order, followed by hyperconjugation, and then least important or the least strong is, not least important, the least strong is inductive effect. One important exception is that in case of halogens attached to conjugated system like benzene, minus I is more dominant than plus M. Okay, benzene acts, sorry, if a chlorine atom is there, then that will act, mostly it can act to withdraw electron because it is more electronegative. So it was supposed to show plus M effect, but in that case, in case of chlorine, what will happen? Rather than plus M, it will dominantly show minus I effect. Okay. These electronic effects have a very vast application and impact on various properties of organic molecules. Let us try to understand the effects of some of these on the stability of carbocation, effect on acidity and basicity. So in this video, we will be dealing up with carbon, like stability of carbon intermediates and acidity as well as basicity, strength of acidity and basicity of organic compounds. Okay. So first is effect on stability of carbon intermediates. Now, in order to understand the stability of any charge species, keep in mind that more is the delocalization of the charge, greater is the stability. Basically, if there is any charge development, suppose understand it like that, carbon is like us, okay. We as human beings, if we are in certain trouble or worries or we are sad, what we like to do? We like to share it with somebody, right? We want to like discuss it with somebody and sort things out. So carbon is like that only. If it is developing any charge on itself, it is like to delocalize or spread it out. It does not want to keep it entirely to itself. Okay. So electron donating groups which has plus I, plus M or plus H hyperconjugative effect, hence stabilize the electron deficient species like carbocation and free radicals. On the other hand, electron withdrawing groups like -I or -H. Why not minus M? Why not -H? Because hyperconjugative structures or hyperconjugation can never operate in withdrawing electrons. It is always in a system where it has to donate its sigma bonds to a deficient atom. So there is no effect called -H. Okay, keep that in mind. So basically, electron donating groups or the electron donating effect stabilizes the carbocation and free radical. Those are deficient in electrons. And electron withdrawing groups, they stabilize the electron rich species, that is carbanions. Now, stability of carbocations. The carbocations are generally unstable due to electron deficiency or a positive charge on the carbon atom. But any effect which decreases the positive charge on this carbon increases their stability. The relative order is 3 degree, greater than 2 degree, greater than 1 degree, and which is further greater than the methyl group. Okay, this is the order. Why so? See, this can be explained as, first of all, we'll start from the bottom, which is inductive effect. Now, methyl group shows a positive inductive effect. That means it is donating group. It is a donating group. It donates electron density to the deficient carbon atom, right? So, if I see the tertiary structure, then there are 3 methyl group attached to the carbon atom. As a result, electron donating effect is maximum. And this effect gradually decreases when we move on to 2 degree followed by 1 degree. And in case of methyl, there is least effect observed because to the methyl group, there are no other alkyl groups associated. Therefore, inductive effect is one factor which can account for the stability of this 3 degree carbocation, right? Now, if I look at the, here, the plus I effect of alkyl group pushes 2 electrons towards the electron deficient carbon, which may be summarized as, the order is like this. However, carbocations like allyl and benzyl are stable due to resonance. If I see allyl and benzyl, that means the presence of double bonds. Okay, if I'm seeing this structure, then CH2 double bond CH bond CH2 positive. Now here what happens, this pi bond is the weakly held electron cloud. So this pi bond has the tendency to resonate in between these 2 carbon atoms. So its structure can be like interchangeably expressed as CH2, CH, CH2 double bond and positive here. So there are 2 resonating structures possible for this allyl carbocation, and this accounts for the stability of this one. Now, if I see the benzyl carbocation, of course, the benzene ring is a whole conjugated system and it is highly electron rich. Therefore, it can stabilize the positive charge that is developed over the methyl or alkyl carbocation here by the 3 resonating structures. And we know greater the number of resonating structures, greater is the stability. So, therefore, benzyl carbocation is highly stable due to resonance. Now, if I look at this, the stability of carbanions. Now, carbanions are the electron rich species, right? So, carbocation was an electron deficient species. That groups, those tried to donate the electron density towards the carbocation, made it stable. In case of carbanion, what will happen? The groups which try to withdraw electron density from the carbanion will account for the stability of carbanions. So, the carbanions are unstable due to negative charge on carbon atom, and any factor which increases this negative charge makes them more unstable. Therefore, the groups with a plus I effect decrease their stability, but rather minus I, the ones that pull electrons from the carbanion, they increase their stability. Okay, so plus I effect decreases their stability, hence the order of stability is the reverse of carbocation. Now here what was happening? 3 degree was more stable, here 3 degree is least stable because of greater number of electron donating alkyl groups. The order is just the reverse of carbocation. Now, due to the destabilizing plus I effect of alkyl groups, the allyl and benzyl carbocations are however more stable. Why? Due to resonance. Here what happens? If I see methyl CH3 minus, then the minus is entirely residing over one particular carbon. The electron density is residing over this carbon only. It cannot delocalize its charge. But if I see CH2Cl, then what happens? Here Cl acts as an electron withdrawing group. It's an electronegative group. So that's why it will somehow show minus I effect. Therefore, this negative charge is now not entirely present upon this carbon atom. Rather, it is shared by another chlorine atom attached beside it. Now, if I see the allyl carbocation, here this resonating structure, this double bond, negative charge can become the double bond, and the double bond can become the negative charge. So, this shows the stability of carbocation, carbanion. Now, if I compare the benzyl, again benzene ring can both act as an electron donor as well as electron acceptor. That is a unique tendency of this benzene ring. So as a result, what happens? This negative charge becomes double bond here, and this double bond shifts onto one carbon. This process continues, and I get 3 resonating structures of benzyl group. Therefore, these resonating structure account for the stability of benzyl carbanion. So, although the order in case of alkyl groups is reversed, but in case of allylic and benzylic compounds, the order remains the same as that of carbocation because of resonance. Now, we will see carbon free radicals. Again, free radicals are electron deficient species. So, their stability or the factors which affect their stability are pretty much same as that of carbocation. Free radicals are unstable due to unpaired electron, and electron density at the carbon center and electron donating effect increases their stability. So, the order of stability is same as that of carbocation. This is due to the increase in the number of plus I effect of the alkyl group. The order may be 1 degree, greater than 2 degree, greater than 3 degree. However, carbon free radicals like allyl and benzyl are stable due to resonance. Okay. So, you can see the resonating structures of allyl and benzyl. These are same as the carbocation ones. Allyl and benzyl carbocations have greater stability than tertiary and secondary and primary free radicals. Thus, the overall stability is allyl or benzyl greater than 3 degree, greater than 2 degree, greater than 1 degree. And this is same as the case of carbocations also. Okay. Now, if I see acidity. Now, what do you mean by acidity? Like acidic strength is determined by the tendency of donation of a proton H+, because we know that by the definition of acid, acids are those substances those have a tendency to donate an H+ ion. So, in a molecule having an electronegative atom joined directly to a hydrogen atom, the acidity is affected by the following 2 factors. First is ease of deprotonation, means with what ease it can liberate a H+ ion. And the second is stability of the conjugate base. Like after a compound has lost one acid, it had the tendency to lose one acid, the H+, that's why it was an acid. After the loss of acid, now it has the tendency to gain an H+. So now after the loss of a proton, the remaining substance is the conjugate base of that acid. So an acid can be, or a substance can be said to be acidic if it satisfies 2 conditions. First, if it is able to lose the H+ more easily, and secondly, after losing H+, it becomes stable. It has no more urge to accept or grab that lost H+, right? So there are 2 factors which affect the acidity of any compound. One is ease of deprotonation. Higher the electronegativity of the electronegative atom, higher is the acidity. Higher electronegativity ensures easy deprotonation. Why? What happens? Suppose I am saying an atom and H, then what happens? Being highly electronegative, it will try to pull this electron clouds towards itself, and it will make the H+ free for removal now, right? So, if the hydrogen is attached to a more electronegative atom, it is a highly acidic proton. Okay, the next is stability of conjugate base or the ion which is being formed after the loss of H+. So, the conjugate base must be stable. Higher electronegativity helps in the stability of an ion. Okay. Next is both these conditions are enhanced by introducing electron withdrawing groups, because after the loss of H+, what is left behind is a negative charge. So, if that any group which is present which withdraws this negative charge or which delocalizes this negative charge, it will add up to the acidity of that particular substance. So both these conditions are enhanced by introducing electron withdrawing group which has minus M, minus I or minus H as such is not there, and decreased by electron donating group which is plus M, plus I and plus H. Remember that second condition is more dominant than the first to arrive at the conclusion. Hence, if two are opposing, we must not rely on the second one. We must look at the first one, that is, which is electron withdrawing. For example, if I am comparing the acidity of phenol and orthometanitrophenol, first of all, identify the differentiating groups amongst all. In the framework of phenol, the nitro groups at different positions are differentiating groups which are responsible for different acidities of these molecules. Now next, if you look at the structures, in case of phenol, what is happening? After the loss of H plus, which is left behind is a O minus. Okay, this is a negative group or a phenoxide ion. Now here what is happening? In case of orthonitrophenol, after the loss of this H plus, there is a negative phenoxide, but here this nitro group is showing minus I and minus M effect, okay, which is intramolecular hydrogen bonding. As a result of which what happens? It does not allow this group or this liberation of this proton to go to further extent. Now in case of second one, that is, or the third one, which is metanitrophenol, here only minus I effect is shown. In case of paranitrophenol, minus I as well as minus M effect is shown. Okay, here nitro group acts as the electron withdrawing group. So any group which withdraws electron charge or electron density towards itself, what it will do? It will decrease the electron density around oxygen atom. Now as a result of which what will happen? The electron density around oxygen atom will be less. As a result, oxygen will be less electronegative. As a result of which what will happen? It will not hold or it will not pull the electron cloud towards itself, and it will not make the H plus more available for donation. Therefore, first of all, if I compare this nitro compounds with phenol, then phenol is more acidic as compared to this nitro things. And again, if I see the ortho, meta and para, then what will happen? Ortho will exert a hydrogen bonding. This will not make the nitro or hydrogen group available for donation. So what will happen? This will show the least acidity. Again, if I compare the meta and para, in case of para, there are two destabilizing effect. One is minus I and minus M. So this will be further less acidic, followed by the para thing. Okay. Same is the case of basicity also. So basicity means electron accepting or proton accepting tendency. So any effect which are opposing to this will lead to the strengthening or the greater strength of bases. Okay, so basically effect on acidity and basicity are pretty much the same, but they are just opposite to each other. So in this video we were dealing with the stability of carbocations and the strength of acids as well as bases. I hope the electronic effects and how we can use the electronic effect to explain the stability of various organic compounds are clear to you. That's all for this video. Thank you so much.